Have you ever stopped to wonder what you are truly made of? Deep down, smaller than any cell, smaller even than an atom's nucleus, lies a universe of tiny fundamental particles. For a long time, we thought we had a neat and tidy map of this inner space, but recent discoveries have torn up that map. Just last year, in a historic first, physicists observed that the quarks inside particles smashed together at incredible energies and showed signs of quantum entanglement. This ghostly link, once thought to be a feature of separate, distant particles, is happening right there inside the building blocks of matter. It's a profound hint that the world within the atom is far stranger and more connected than we ever imagined. To find these secrets, scientists used the most powerful machine ever built, the Large Hadron Collider, or LHC. Buried deep underground beneath the border of France and Switzerland, it is a magnificent 27-kilometer ring and complex detectors. Its job is simple in concept, but breathtaking in scale. It accelerates tiny particles, like protons, to almost the speed of light and smashes them into each other. These collisions recreate the fiery, energetic conditions that existed just moments after the Big Bang. In the flying debris of these cosmic-level impacts, we get a fleeting glimpse of particles that haven't existed naturally in the universe for billions of years. So, what are these particles the LHC is hunting for? Many of them are a type of particle called a hadron. The word might sound unfamiliar, but you are intimately acquainted with them. The protons and neutrons that form the nucleus of every atom in your body, in the air you breathe, and in the distant stars are all hadrons. For decades, the rulebook was simple. Hadrons were either made of 2 quarks or 3 quarks. That was the law. It was a simple, elegant model that seemed to explain the matter we see all around us. We thought we understood the family tree of matter, with its neat branches and predictable members. But nature, it turns out, is more creative than our rulebooks. The news coming out of the LHC has been nothing short of revolutionary for particle physicists. The particle zoo, the collection of all known particles, has welcomed some truly bizarre new residents. Back in the summer of 2022, researchers at CERN announced a discovery. Not one, but 3 new exotic particles at once. Among them was a new kind of pentaquark, a particle made of 5 quarks huddled together. This wasn't the first pentaquark ever found, but its discovery confirmed these 5 quark arrangements are not just a fluke. They are a legitimate, if rare, way for matter to assemble itself, a new blueprint for building particles. These discoveries are the result of sifting through unimaginable amounts of data. Each time protons collide in the LHC, sensors record the trajectories, energies, and identities of the particles that fly out. Most of these are familiar characters, pions, kaons, the usual suspects. But every now and then, a particular combination of decay products suggests something new was created for a fraction of a second. The new pentaquark, for instance, revealed itself through the specific particles it decayed into. To delve deeper into this new territory, scientists have given the LHC a major upgrade. Its current phase, Run 3, began in 2022. The machine now smashes particles at an unprecedented 13.6 trillion electron volts. This energy increase is crucial. Einstein's equation E=mc2 shows energy can become mass. More collision energy means higher chances to make heavier, elusive particles. Particles we couldn't form at lower energies may now appear. It's like turning up the heat on a cosmic stove. We can cook new ingredients of the universe. Detectors have also been upgraded to be faster and more sensitive. That matters because the most interesting events are incredibly rare. The search now includes long-lived exotic particles. Most exotics decay instantly at the collision point. But some theories predict particles that travel a few centimeters before decaying. Spotting a displaced decay would be a game changer, a sign of new physics. Another tool, a related breakthrough announced in August 2025. A very rare Higgs boson decay was observed. The Higgs is the particle that gives others mass. Studying its decays tests the standard model with extreme precision. If the Higgs decays unexpectedly, it could indirectly reveal unseen particles affecting it. These avenues form a web of clues. A rare Higgs decay might point to a particle mass. Run 3's direct searches might then create that particle. The hunt for long-lived particles gives a different angle to catch it. It's a multi-pronged attack. So we find a new particle with 5 quarks instead of 3. It lives for a fraction of a second and then vanishes. It's a fair question to ask. Why does this matter? The answer is that these discoveries are fundamental to our quest to understand the universe. Every exotic hadron we find is a new test for our theory of the strong nuclear force, called quantum chromodynamics. This theory has worked beautifully for decades, but these new particles are showing us its edges, the places where our understanding is incomplete. They are stressing the model in new ways, forcing us to refine it and perhaps even overhaul it. Imagine our current understanding of matter is like knowing bricks can build simple rectangular walls. Finding exotic hadrons is like discovering those same bricks can build arches, domes, complex mosaics. It doesn't mean our knowledge of walls was wrong, but it reveals the principles are far richer and more versatile than we knew. An exotic hadron with 5 quarks might be structured like a miniature solar system, with 2 smaller particles orbiting each other. This would tell us the strong force can act not just as a glue, but also as a bond, creating particle molecules. Beyond the strong force, these discoveries could point the way towards solving the biggest mysteries in science. The standard model is magnificent, but it's incomplete. It doesn't explain gravity, it has nothing to say about dark matter, and it doesn't explain why there's so much more matter than antimatter. New particles or strange behaviors could be the first whispers of a deeper theory. They could be the first tangible links to new physics. Ultimately, this is about the human desire to know where we came from and what the world is made of. The protons in every atom in your body follow the same rules the LHC is testing. How do scientists become confident that they have truly found something new and not just a statistical ghost in the machine? The process is incredibly rigorous. It begins with collecting colossal amounts of collision data, trillions upon trillions of events. Sophisticated computer programs then sift through this data, looking for the specific signature of a new particle's decay. This signature is often a bump in a graph, a small excess of events at a particular energy. This is the first hint of a discovery, but it is far from the final word on the matter. Once a potential signal is seen, the real work begins. Scientists must painstakingly rule out every other possible explanation. Could it be an error in the detector? Could it be a known process that is simply mimicking the signal of a new particle? Teams run simulations, cross-check their analyses, and look at control regions in their data where no new particle is expected to appear. Atlas, CMS often act as rivals and collaborators, independently trying to confirm or refute each other's findings. A discovery is only claimed when the statistical evidence is overwhelming, typically at a level of certainty known as 5 sigma, which means there's less than a 1 in a million chance the signal is a random fluke. Even with all this caution, we must remain honest about the nature of scientific exploration. Not every exciting bump in the data grows into a confirmed discovery. Sometimes, as more data is collected, a promising signal can fade away, revealed to be nothing more than a statistical fluctuation. This isn't a failure. It is an essential part of the scientific method. It is how we ensure that when a discovery is finally announced, it rests on the most solid foundation possible. The path to knowledge is paved with these careful, methodical steps, and patience is just as important as brilliance. And so, the search continues, filled with both hope and humility. The LHC's Run 3 is still gathering data, promising a flood of new information over the coming years. Each new result from the frontiers of particle physics shows us that the subatomic world is a place of endless wonder, still holding on to its deepest secrets. We are explorers in a vast, invisible landscape. We don't know what we will find next, A new exotic hadron, a crack in the standard model, something so unexpected it has no name yet. But what is certain is that the journey into the heart of matter is far from over, and the view is getting more spectacular with every step. By discovering how quarks combine in exotic ways, we learn more about the fabric of reality. We are peeling back another layer of the cosmic onion, more complex, more elegant, more surprising than we dared to dream. It's a story about all of us, written at the smallest possible scale. Each clue, from quark entanglement to rare Higgs decays and long-lived particle hunts, brings us closer to understanding matter, forces, and ourselves.